introduction while I get my screen ready to share.
I have the lights. Yeah. So we can see your slides nicely.
Oh yeah, right. That always helps. Oh wait, okay, so yeah, thanks so much for the introduction. It's really lovely to be able to give this seminar. I haven't really met many people in the department, so I'm very excited to have a bit of conversation about some of the work that we've been doing over the past little while. Since this is a virtual talk, I have put a few of these question pause slides in as a feature to sort of like give ourselves a little bit of time to think and pause and breathe, because I know an hour-long virtual seminar can be taxing, both to give and to receive. So hopefully we can kind of break things up and have a little bit of a chat in between some of the topics that I'm going to talk about. So since I have not had the pleasure of meeting many of you, I wanted to just give you a quick overview of sort of like my astronomical identity. So first and foremost, I think of myself as a binary population simulator. And what that means is, in practice, a lot of my time is spent developing open and accessible software and making studies with very easily reproducible results. My ideal scenario is that somebody can read my paper, access my code, access my data, and not have to send emails, except for clarifying emails, so that it's really public and available, so that we can all move the field forward together. One of the first things that I started working on as a graduate student and have continued to work on is gravitational waves as a topic. I'm not a person who thinks about detecting them, searching for them, even analyzing the data too much. Instead, I like to think of using gravitational waves as a tool to understand binary stars. That's really like the meat of what I like to think about is binary stars. And more recently, I've been moving towards trying to think about how we can use the whole host of electromagnetic surveys that are currently online and plan to be online over the next 1 to 5 to 10 years to study enormous binary populations with like really fantastic time resolved data that we can use to study binary populations at these intermediate evolutionary phases. So that's a little bit about me. If you have any questions about any of this and you want to chat offline or anything like that, definitely drop me a note. I'd love to chat more with folks. Okay, so now begin the actual talk. So I like to start every talk that I give with a reason to convince people that binary stars are exciting and it's not a dead field. I think for a lot of people who grew up doing theory, if you read binary star evolution papers, many of them are citations from the 1970s, because people like Paczynski and Ron Webbink and others really thought a lot about this analytically in the 70s. And then there wasn't a lot of data specifically oriented to binary stars to really get down and understand what are the physical processes that are shaping binary star populations. So many people don't really think about binary stars too much, but you should be interested in binary stars either because they are an actual critical component of your science, or they are a limiting noise source. And so much of the science that's being done in astronomy are running into binaries as a noise source. And if you want to see an example of this in action, we used the decadal survey process in 2020 to try to convince people that like the field of binary stars is really about to become a just exploding field, because there are basically any astronomical study that's going on, the binary stars are either a source, like in multi-messenger astrophysics, like I work on, or compact object formation, or a very annoying noise source. So for example, exoplanet populations, if you want to study thousands of exoplanets, your biggest false positives, your biggest source of false positives are binary star populations. Similarly, for folks who are studying stellar streams to try to find clumpy dark matter, one of their biggest systematics is not being able to account for binary star motion and how that affects the motion in the stream. So one of my favorite things to do when I can visit departments is kind of like play a bet and see if folks can come up with a field of astronomy that isn't at least tangentially dependent on binary stars. So now that everyone believes me that we should all be excited about binary stars, even if you're not just like really excited about Roche loads like I am, let's all get on the same page of what the deal is with binary stars from an observational perspective. So there have been several studies over the past decade to decade and a half where we've started to get real, like sizable populations of binary stars. And the largest population so far is one reported from the Apogee survey, where Adrian Price-Whalen studied the entire survey, assuming that there were potential single spectroscopic line binaries. And he tried to fit the orbits of all of the Apogee survey to see how many binary candidates there are. And there is a 30,000 candidate size catalog. So 30,000 binaries potentially exist in the Apogee catalog. All of these studies together have painted a picture where we can now pretty quantitatively say that most massive stars and many lower mass stars are born with a companion. And this is very exciting to people like me who are interested in binary star evolution, because having a stellar companion to a star, a binary, introduces the potential for interactions between the stars. And that's some really, really fun physical processes that you can dig into. Some of these processes include things like mass exchange and common envelopes. If a massive star explodes, that supernova explosion can alter both the mass in the system of the binary, but as well as the orbital properties, including adding things like natal kicks to compact objects. You can also think about how binary stars or double compact object binaries evolved due to the emission of gravitational waves, or you can consider things that are happening interior to the star and thinking about how stellar interiors actually affect the orbit of the star, of the binary itself, with things like tides and magnetic braking. The way that I like to study binary stars is through the development of a population synthesis code that I lead the development of. It's called Cosmic. Cosmic is a Python-based population synthesis code. It's completely openly developed in Python. It's on GitHub. We've got tons of documentation and examples in the hopes that people will be able to use it. One thing that we're very excited about is a recent release where we coupled Cosmic, which does isolated binary stars, to a globular cluster dynamics code called CMC, so that we can make self-consistent comparisons between binary stars formed in a galaxy in an isolated environment versus stellar populations formed in dense stellar environments like globular clusters. I want to very quickly acknowledge the fantastic team of people that has worked together to produce the release of Cosmic. It was a really big effort to get everything together, get the documentation together. And one person who's an absolute shining star is Scotty Coughlin, who's now not an astronomer anymore. He's actually moved on to be software full time, but he's really helped us think about user interface and making sure that people can pick up the code and run with it. I want to highlight very quickly just some of the types of science that Cosmic has been used to inform and study. And in particular, one thing that I want to point out is that Cosmic has been used to study stellar populations of stars that aren't compact objects. It's been used to study populations of common envelopes, like specifically produce common envelope rates, as well as you can see here, much of what we're thinking about right now is forecasting for double compact object populations like binary black holes or white dwarfs or X-ray binaries and the lot. The other thing that I want to highlight very quickly is the studies marked in green here. These are actually studies where there were no Cosmic developers. So this is really like open source, open software in the wild where people picked up Cosmic, did studies, and I learned about those studies on the archive because they cited our paper. So it's a really gratifying and exciting time to see what's coming out of Cosmic. So for the science portion, now that I've told you a little bit about the tool that I've developed and what what's gone into it, what it can be used for, I want to talk a bit about two specific science cases of things that I'm very excited about. And the first is LISA. So this is much of the LISA science case on a single slide. And I don't want to scare you off. This is a very, very busy slide. And I'll talk a little bit about what the axes are on this slide a little bit later on. But what I want you to focus on is that this millihertz frequency regime of gravitational waves, LISA is a future space-based gravitational wave detector, is extremely rich with sources. So we've heard about detections of merging double compact objects from LIGO, Virgo, Kagra folks, the ground-based gravitational wave detectors. LISA has an enormous host of sources that will be producing gravitational waves in the band. In particular, there is this source class of this gray versus and purple cloud of points. Those are galactic double compact object binaries. I'll talk a lot about that in a little bit because that's my main focus. But there are also other very exciting sources. So these red bands that you see here, these are merging massive black hole binaries out at redshift of 3. If you have a merging massive black hole that is 10 to the 8 solar masses, 10 to the 9, you can really observe LISA will be able to observe these systems at very, very high redshifts, enabling really, really interesting potential cosmological science. In these red bands here, these other red bands, these are called harmonics. So this is the signature of a single stellar mass black hole that is orbiting a supermassive black hole and actually physically tracing out the space-time of a supermassive black hole. And this happens over like a yearish long time scale. So it's a really, really rich space to be thinking about gravitational waves in. Unfortunately for us, it's 2022, so LISA is still a cartoon. It's not fully built yet. LISA's planned launch is in 2035 at the moment. It was 2034 until the pandemic hit. So a 1-year pandemic slip is actually pretty shockingly good for an enormous space mission like LISA. LISA is very different from ground-based detectors because it has 2.5 million kilometer long arms. It definitely has to orbit in space. It orbits on an Earth trailing orbit, but around the sun, a heliocentric Earth trailing orbit. And the size of its arms translate to a gravitational wave sensitivity that puts it in the region of observing orbits that are 90 minutes to 20 seconds. So very different from merging stellar mass compact objects like ground-based detectors are sensitive to. The way that LISA works is there are test cube masses that are literally like 2 inches by 2 inches by 2 inches on a side. And they hang out in these little spacecraft here. And as gravitational waves pass through, they stretch and squash this laser light here. And it's actually the buildup of phase that changes as the gravitational waves pass through that help you observe the stretches and squashes. It's the laser light phase that we observe. What else do I want to say? The largest noise source of these detectors can be understood through sensitivity curves. So this is, instead of thinking about telescopes as like photon buckets, picking up photons, we think of gravitational wave signal to noise ratios as where sources fall on this sensitivity curve. So on the y-axis, I'm showing the amplitude spectral density, and this is sort of like a measure of how much stretching and squashing there is per root frequency, since it's an amplitude. And on the y-axis is gravitational wave frequency. The shape of this sensitivity curve is completely defined by the characteristics of the detector. So at low frequencies, this is a function of how well you can actually measure the position of the test masses in each spacecraft over very long periods of time. The period of time is basically 1/10⁵ seconds. So being able to precisely measure the position of a test mass on day to month long timescales is what's sort of fixing this increase in noise or decrease in sensitivity as you go to low frequencies. At the bottom, this is how well you can actually keep the test masses isolated from like external conditions. One of the biggest sources of noise for LISA is actually solar radiation pressure. So that's kind of an interesting, weird collision of like solar system physics and gravitational waves. And then on the right here, the sensitivity actually degrades at high frequencies as well. And that's because the actual physical wavelength of the gravitational waves starts to become smaller than the size of the LISA arm lengths itself. And you can actually see the effects of this in this beating pattern where you get to integer multiples of those arm lengths. So this is how we measure sensitivity. You can see on the y-axis here that the strain is just astronomically tiny. We're talking about 10 to the minus 18 to the minus 19, really small numbers. But luckily for us, and luckily for people like me who want to study binary stars with LISA, Close double stellar remnants in our galaxy are fantastic gravitational wave sources. We can compute the gravitational wave signal of, say, a double white dwarf binary like this one. It is a function of the chirp mass of the binary, which is a combination of the two masses in the system, the orbital period and the distance. And you can see here that number, 5 times 10 to the minus 18 for hour-long orbits within our galaxy. That's going to put you on the LISA sensitivity curve. One of the fun things about close double remnants in the galaxy is we can actually see them with telescopes too. And so we actually know of something like a couple of dozen of close double white dwarf binaries that exist in the Milky Way at short periods. And we have their distances because of missions like Gaia that can give us the distance to the double white dwarfs. So we already know that there are sources out in the galaxy today that once LISA flies are radiating in the band. We call these verification sources because once LISA turns on, with like a month of detector time, you can pick out these systems specifically and say, we know that LISA is working exactly as we expect because we have predictions and we can verify them. All of the figures that I used, that I have shown you so far have used this tool, legwork, that I developed with a fantastic first-year grad student, Tom Wag. Our goal here was to take any and all calculations that you may do with a stellar mass system in the LISA band and put them into a package. The reason for this is because the calculations can be done analytically, so it's lightning fast, but they're really hairy. There's lots of factors of 2 and 96/8 and powers. And so the literature has a ton of typos, which is totally understandable because it's a huge pain. But we put it all together, wrote a paper so that folks can use it and have ease of use to see whether or not their favorite sources are detectable. One thing that I want to highlight is that we used this lovely latex package developed by Rodrigo Luger. And it produces a framework for you to actually take all of the code that you use to produce the figures in the package and run that code in real time to write your paper. So it's the most openly reproducible science that I have found so far. It's like, it really helps you to produce reproducible science. So I would encourage you to check it out. Okay, so for LISA, I've said I showed you before that there are tons and tons of double white dwarfs in the galaxy. And one of the things that we talk about a lot in LISA is this sense of a foreground of sources and resolved sources. So the reason for this is a little bit technical. And so I want to go into it a bit so that you can at least leave knowing what people mean when they talk about a double white dwarf foreground or background or a resolved population of double white dwarfs. So what I've drawn here is a cartoon of, say, a bunch of double white dwarfs out in our galaxy. Maybe there's some double compact objects in there too, but by and large, the galaxy is mostly filled in terms of double stellar remnants with tens of millions of double white dwarfs. If you think about LISA in the simplest terms, it really is just a set of buckets in frequency. And if a double white dwarf is radiating gravitational waves in a frequency bucket, LISA observes them based on what their emitted orbital frequency is or gravitational wave frequency is. By virtue of how gravitational wave emission works, we actually just take all of the double white dwarfs, assign them to the bucket that they fit in. And because all of the double white dwarfs and double compact objects in our galaxy are driven just by gravitational wave emission, we can write down the dependence on the gravitational wave frequency itself to show that you are much, much, much more likely, if you are a binary in the galaxy, to find yourself at low frequencies rather than high frequencies. And that's because at low frequencies, your gravitational wave evolution is very slow. And at high frequencies, your gravitational wave evolution is very fast. And so it's very unlikely just to observe systems at these higher frequencies because they zip through the band quite quickly. There's another competing factor to this, which is LISA's frequency sensitivity. Broadly speaking, a good rule of thumb is that it's just 1 over its observation time, so something like 1 over 4 years. And that's the LISA frequency resolution that you have. When you think about this set of bins, in terms of that frequency resolution, what that means is that there are 10,000 buckets at the lowest end and 10 million buckets at the highest end to put each double white dwarf into. And so what that ends up doing is what you end up finding is that you have more double white dwarfs at low frequencies and fewer bins for LISA to resolve them into. And so at low frequencies, you get a bunch of overlapping signals, while at high frequencies, you get fewer overlapping signals. The way that we actually forecast what we expect LISA to see is a very similar process to all binary population synthesis studies. We initialize a stellar population. We evolve them one by one using our favorite PopSynth code. Here I'm showing you a whole host. There's tons of PopSynth codes. I only told you about Cosmic because that's the one that I'm a part of, but there are a bunch of them. The ones in blue are publicly available, but Cosmic is the only one that you can access through Python. So you initialize your population, send your binaries through with Cosmic, evolve them from zero domain sequence to the present day, collect your double white dwarfs and repeat. Once you have all your double white dwarfs, you add up their gravitational wave signal with something like legwork, and then you can actually put what the gravitational wave population of double white dwarfs in our galaxy looks like. And so each spike that you see here is an actual double white dwarf at that frequency that's radiating gravitational waves with a strength of the height of the spike. One thing that I want to point out here is that at 10 millihertz, double white dwarfs actually start to interact because one of the lower mass white dwarf will fill its Roche lobe. We tend to pull these systems out and treat them separately because Cosmic doesn't treat them in as high a resolution as you probably should. The other thing that I want to point out is that roughly below 1 millihertz here, this is where double white dwarfs, if you exist in this frequency band, you'll broadly be unresolved. And that just means that there are more than one double white dwarf in each frequency band radiating over the top of each other. But above 1 millihertz, they are resolved. So as I said before, the vast majority of the reason why this happens is because there are many fewer bins at these low frequencies and many more double white dwarfs, whereas above a millihertz, there's something like 10,000 double white dwarfs and millions of bins to put them in. So one of the studies that we've done recently was just taking a step back and saying, okay, this is how we simulate our double white dwarfs. What can we kind of like tweak to understand, to see what we can learn when LISA flies? And one of the things that we know is that the assumptions that you make for the zero age main sequence population very strongly influence the double white dwarfs that you produce in your simulations at the end. And those assumptions are broadly driven by empirical data sets. So we know, for example, that the IMF is tilted towards low masses. We can look out at the binaries in the apogee catalog and other catalogs to make assumptions for things like uniform mass ratios to secondary stars, uniform eccentricities, log normal orbital periods. And then this is the big assumption that has been sort of like colloquially decided for quite a long time, that the binary fraction of stars is 50%. However, we have data. We live in 2022. We have data, large data sets of binary stars, 30,000 binary stars. And one result that started to really firm up over the past 5 to 10 years is that the close fraction of sun-like stars is very anti-correlated with metallicity. So you can view it from two different lenses. These are, this is Max Mo's paper and Christine Mazzola's paper. And what you see here is that at low metallicities, the idea of a 50% binary fraction isn't completely wild. It seems fine. But at near solar metallicities, the binary fraction is actually closer to something like 15%. Right. So we realized we can take this into account in our simulations. And so some work that I did with a fabulous undergraduate researcher, Sarah Thiel, who's at UBC, we took these empirical metallicity dependent binary fraction results, combined it with a cosmological zoom-in simulation of a Milky Way-like galaxy called the latte suite of the FIRE simulations. This gave us metallicity-dependent positions and ages for our zero-age main sequence stars. And then we used Cosmic to evolve them forward to predict what we expect LISA to observe using this empirical binary fraction. Again, I don't have too much time to go into details of what Sarah actually did. She wrote about 1,000 lines of Python code, but it's all here and show your work. So if you want to dig in and look at the paper, see what's cracking in there, you're very welcome to open up our pipeline, see how we did everything. What I want to show you is just the punchline. And what we found is that applying a metallicity dependent binary fraction reduces the height of our double white dwarf foreground by about a factor of 2. So this is illustrated again. Here we're showing a power spectrum density instead of amplitude, but it's roughly the same idea. This is the gravitational wave strain of the double white dwarfs in the galaxy as a function of gravitational wave frequency. In light colors, light blues, we're showing the population simulated with a metallicity dependent binary fraction. And in darker colors, we're showing a population that assumes a 50% binary fraction. And as you can see, just as a function of frequency all the way across the band, there's this reduction in 2. We were pretty surprised that it was so dramatic. We were actually expecting to study the resolved population, and really what our results ended up showing us was that the resolved population doesn't care too much about the binary fraction, but the foreground really cares a lot. We also expanded our study to include several limiting Roche overflow assumptions in our binary evolution model. And so what we're showing here is the fit, this dotted line for several different models. The solid lines, again, are the metallicity dependent binary fraction. The dotted lines are for a 50% binary fraction, and these are just limiting cases. Overall, if you just take the ratio of the two, even varying the size of the LISA population, the number of double white dwarfs that we predict by 2 orders of magnitude, we find that the foreground is robustly reduced by a factor of 2. That means if you have colleagues who are making any predictions at all of sub-millihertz LISA sources, they should take whatever they're using for their simulations to predict the sensitivity of the double white dwarf foreground, or what the height of the foreground is relative to the sensitivity of their source of interest, and they should cut the height of the foreground in half, regardless of what their assumptions are. The other thing that I want to highlight that's very exciting, and we're thinking a lot about for future work, is that by changing our Roche overflow assumptions, we change the size of the LISA population by 2 orders of magnitude. So once LISA flies, we can really use the size of the resolved population and the size of the population itself as a very strong lever arm on these Roche overflow interactions. We haven't dug into that data set yet, but we have a few years since LISA has been flying for about 15 years, but we'll see what happens there. And so this is all I wanted to say about double white dwarfs. I'm going to pause for a second to take a drink. Folks can ask questions about double white dwarfs if they want to. I'm going to move on to black holes. So feel free to shout out if you want to. Yeah.
Can I shout out and say I have a foreground, I am one of those people who has made predictions for sub-millimeter, for millihertz LISA sources using a standard fit for the population of background sources and not cut it in half. So I will do that next time.
Yeah, see if it helps. We were really, it's the fact that it is just so clear across the whole, we're really excited about this. We're trying to get the word out because a lot of people will take entire science cases off the table because you don't think that they're detectable because of the height of this confusion. So it's good to hear that we can help.
Thanks. Katie, this is Tessa speaking, by the way.
Oh, lovely. Hi, Tessa.
Sorry, you can't tell because I'm in a room and I don't have a Zoom name and I've got a mask.
No worries. No worries.
Maybe I'm preempting your next section, but if these results for the double white dwarfs come out from doing a proper metallicity, incorporating metallicity correctly in the zero age main sequence, does that have similar implications for black holes?
Not so much. And the reason for that actually goes to this. So the data that we have at present is mostly just from apogee. That's the vast majority. And this was something I didn't think too much about until digging into the apogee data myself. The apogee data is really only valid for 1 to 3 solar mass stars. So progenitors to black holes being 20, 40, 60 solar masses I'm really hesitant to say anything about what their metallicity dependence looks like. And unfortunately, we don't have enormous catalogs yet to plug in. So I would say for now, I don't think that this has implications for black holes. But maybe in 5 or so years, we'll have more data and we can do a similar type of study for what we expect for the black holes.
Okay. Yeah, so I totally get what you're saying, that there isn't any data to make any statements on. But in terms of the physics that's involved, if there's a strong metallicity dependence in these binaries, that would be super interesting.
Yeah, definitely, because the Milky Way has tons of like metallicity gradient across the stellar populations. Yeah, and you make a good, like, it would show itself for sure in the black holes, I think. Yeah.
I'm gonna ask one more thing. I know I'm hogging the floor here. You say metallicity gradient, so I'm not a galactic astronomer, so metallicity can vary significantly across a galaxy. Is that true?
Yeah. So this, for example, like this is 3 orders of magnitude, and this is solar metallicity. So very low metallicity stars can produce. They're one of the. This is, I'm like. I'm hesitant to go too far into this because it's like a whole field. I don't want to like not give it credit, but at low metallicities, one of the predictions from population modelers like myself is that you get much more massive black holes here relative to black holes with stars that are formed at metallicities here. And that's because stellar winds are actually metallicity dependent, because we think that they're driven, at least in main sequence stars, they're driven through iron lines, more or less. So if you have higher metallicity particles, you actually have like higher electron orbital shells in the molecules in the atmosphere of the star. They can take in light to put the electron orbital like at a higher level, and the momentum transfer there is enough to literally carry mass off of the star. So it's like they call these line driven winds, but it's literally just that there's much stronger winds at high metallicities than lower metallicities, and that limits, we basically have no way to produce like a 25 solar mass black hole at super solar metallicity. So if Lisa only observes 50 solar mass black holes in our galaxy, that's going to tell you that it didn't come from solar metallicity stuff.
Okay. That's crazy that kind of physics at that level from electron orbiting shells can.
Yeah, it's totally it's literally like conservation of energy, like first year modern physics. Like you can calculate the energy in the orbital shell and the energy of light that's being radiated out from the stellar core. It's really fun stuff.
Okay, great. Thank you. I'll stop them. I'll stop hogging.
No worries. There, yeah. So I saw a question from David, and I think that this is a good one to put at the end because we might get off the rails. But so we can talk more about that after, if that's okay.
Katie, can you? I think you're beginning to answer this question, but if one wants to understand why the metallicity is affecting the binary fraction, is this because the metallicity is affecting the mass, which is related to the binary fraction, or is it an extra factor?
So the metallicity it's actually, we think it's, I shouldn't say we, I am not a person who does this science, but Max Moe and Caitlin Crater are people who study star formation, and they think that the reason that this metallicity dependence is coming into the equation is actually because of cooling during the star formation process. And so close binaries are formed through disk fragmentation, while wider binaries, like say 1,000, like actually you can see here, greater than 10 astronomical units, those are actually formed through core fragmentation. So it's a different process. But in disk fragmentation, if you decrease the disk's metallicity, that will decrease its optical depth, and it allows radiation and cooling more effectively. So at low metallicities, you're more likely to get binaries forming, while at high metallicities, you're less likely to get binaries forming.
I see. So it's not directly dependent on the mass. It is an independent factor.
Yeah, that's right. And so the mass actually comes into the equation more from just a data set perspective. It's that apogee is really only sensitive to solar type stars.
Great, thank you.
Yeah, of course. Okay, good stuff. Okay, so I'm going to completely shift the focus here for the last little bit. And this is some work that we've been doing recently to kind of get at how can we study black hole formation in binaries. And the idea here is if you think holistically about binary black hole formation, this is the pathway that it makes. There are phases where you have a detached black hole orbiting a bright star. And so we're kind of trying to really anchor down this lever arm of what we can expect to learn. There's a little burgeoning set of work that we've put out on this. And today I'm going to focus on this blue project with specifically the apogee modeling. From a gravitational wave perspective, the LIGO Virgo Kagra team has dropped 90 pairs of merging black holes and neutron stars into our lap. You can see here that their masses are quite enormous when you're thinking about a merging black hole here, say 40 solar masses up to 50 solar mass, or sorry, 20 solar masses with 50 solar masses is producing, 60, 70 solar mass system. This is such an exciting time. I'm so grateful to the LIGO folks who are, putting out this data. I should say LIGO Virgo Kagra. I'm very North American centric and I'm trying to fix that. But one of the things that as a binary modeler is so frustrating is that there are 90 merging pairs of systems and there are almost 90 formation pathways that you can make them from. And so it's quite difficult to disentangle which channels are producing which systems. I'm not going to talk about this too long, but I have so many thoughts and feelings about this. If you're interested about formation pathways and all of that, please do reach out to me offline. Broadly speaking, just for an overarching description, they're divided into two sets. There's either dynamical formation, where there are physical processes that are going to bring the merging black holes together through dynamics. That happens in stellar clusters, AGN disks. Maybe there's like few body interactions that happen rarely, but are very efficient at making mergers or triples. Or there's isolated systems, and these are things like non-stellar black holes. Maybe there's primordial binary black holes that are formed. There's a bunch of cosmological theories that can come up with ways to produce non-stellar black holes, but they're usually not dynamically put together. Otherwise, it's just isolated binary stars coming from different regimes here. So I'm a person who just does standard normal binary stars like the ones that you can see in our galaxy. There are other channels that, I won't talk too much about, but the punchline here is that really there's so many different ways to produce them. If you are just doing it from a standard stellar evolution perspective, there are some guiding principles that you can carry with you. And one of them is that binary interactions tend to, on the way of bringing you to merger, decrease the size of the orbit. So that means that if you're a detached binary star, you're hanging out in much wider orbits. You have a Roche lobe overflow transfer that brings you potentially closer together. Maybe there's a kick with this black hole when it forms through a supernova that widens the orbit a bit, but Roche overflow interactions really bring you closer together. One other feature of these interactions is actually that the number of binary stars at each phase also decreases significantly. So if, for example, you're thinking of black hole progenitors, their progenitors make up something like 1% of massive star formation. After they've interacted, between 30% and even much more of the binaries are going to, in an interaction, 30% will merge and 90% will disrupt through natal kicks. So this really cuts down on the total amount of stars that are formed. I'm going to skip over X-rays because X-rays are difficult and very hard. The number of merging compact objects, it makes up a tiny fraction of all star formation. And that's just because it takes a long time once you form a double compact object to bring it to merger through gravitational wave evolution. If we want to be gracious and only look at the black hole progenitors, you can play the same game and just think about massive star formation. But again, the merging pairs of binary black holes that are being observed only make up 0.5%. So, and as I said, the number of X-ray systems is actually a huge open question because X-ray modeling is quite difficult. So if you're interested in this and you have opinions about it, please do tell me so that we can put solid numbers here, but I just didn't have them. But if you're interested in studying binary stars like I am, instead of just gravitational waves, this might be a much better population to be considering. And so that's kind of what we've been thinking a lot about, is these detached black hole binaries. The ones that I'm going to talk to you about today are systems that are characterized through radial velocity measurements. What that means is that you measure the radial velocity of the system, and it's a function of this luminous companion to the black hole, as well as its orbital period, semi-major axis, and eccentricity. You can measure as it orbits the phase F here, and there is this inclination degeneracy that comes into play. But the punchline is that if you have a well-characterized radial velocity system, you can actually characterize the black hole's mass inside of the orbit. If you measure, for example, like a radial velocity semi-amplitude orbital period and eccentricity. Why am I showing you this particular color? The reason for that is because there are black hole candidates already in the apogee data set of 30,000 binaries. And just a little bit over a week ago, there was another candidate dropped on the table. I put a question mark here because this new system isn't peer reviewed yet. There's still maybe some open questions here, but there are candidates. These two have really stood the test of time so far over the past few years. And the thing that I really want to point out here is the mass of the black holes is sitting like at 3 solar masses. That's very different from the mass of the merging black holes being detected by gravitational wave detectors on the ground. Those are more like 30, 40, 50, 100. 3 is a completely different parameter space, so it's a really fun data set to play with. The other thing to look at here is that their orbital periods are enormous, 80 days. That's so much wider than what you would expect to be able to observe from gravitational waves. So it's a really complementary population. And the big question, which I've been not said yet, but alluding to, is what does it actually mean? We have this data set of apogee binaries. There's 30,000 binaries with properties that we can compare to, and 2 or 3 candidates. Is there some physics that we can try to understand better by using these 2 facts? And so to get at that, we tried to simulate as faithfully as possible the apogee catalog of systems using COSMIC. I'm doing this with Adrian Price-Whelan, Nej Frankel, and David Hogg. So what we've done here is just really try to get as close to we can as producing a synthetic apogee. That means that we're using a galactic thin disk model that Nej put together based on apogee stars. That's going to assign the ages, metallicities, and positions of our zero-age main sequence stars. We evolve forward with COSMIC, and we have a couple of binary evolution model variations, and this is where we're going to try to understand some physics. And then we apply the exact apogee catalog selection that Adrian applied when he built the binary catalog, and that includes using orbital selection with his orbit fitting code, the Joker. It's everyone calls it the Joker, which is it's awful that Adrian named it the Joker, and so we have to try to convince everyone to say Joker. The reason for it is because it's after Johannes Kepler, the Kepler orbits. Just kind of a funny thing. Okay, so let's see. So we made the binary population, and first we just wanted to look at, can COSMIC reproduce trends that we see in the apogee catalog that Adrian produced? And one thing that we just basically compared synthetic figures to his data set. We do very well in reproducing the main sequence binary fraction trends through our selection. So that's quite good. We feel pretty good about that. We actually have a harder time fitting the giants. And that is probably because there's physics happening here. We predict fewer low log G, so fewer really puffy giants. And that means that maybe in our cosmic models, we have interactions occurring more prematurely than is actually happening in the galaxy. This is something that we are trying to dig into now, but we don't have any clear results yet. When thinking about the black hole population, I'm going to show you a bunch of figures that look a lot like this. Our model variations are changes for natal kick strengths, which is, we have 3 models that are broadly applied in population synthesis studies, but the one to really pay attention to here is either no kicks or kicks that are as strong as kicks derived from pulsars. So this is basically 0 black hole kicks or very, very strong kicks, and they increase from left to right. The other thing that I'll show is on the y-axis, this is going to be the mass of the luminous companion. X-axis is mass of the black hole. And then we have our 2 candidates on there. And then finally, the color is basically showing you the density of what our single apogee catalog predicts. I'm going to show you 2 sets of models. We assumed either that the minimum mass of the zero-age main sequence stars is completely uncorrelated with the primary mass, or that they're correlated and there are minimum mass ratios. Let's just dig into that. So our punchline result is that from our apogee predictions, just our synthetic catalog, we predict 1.5 plus or minus 2. So the physical number itself, we don't really have any tension in our models with. But what we do find is if you either have an uncorrelated minimum secondary mass or a correlated mass ratio based secondary mass, you either have to have a very low minimum mass ratio or a low minimum secondary mass to reproduce the observed candidates. The other thing is that if you have basically any natal kicks at all, we really can't reproduce these systems. So what we're finding is that black hole kicks are strongly ruled out from our models. And that is, we've not really seen any of, this is sort of in tension with what you would expect from predictions trying to match LIGO, Virgo, Kagra, or X-ray binaries. So that's kind of fun. The other thing that we find is that the candidates seem to be, curiously, if you instead do the luminous companion mass versus its metallicity, the candidates all seem to be lower in metallicity. And so that's something that we're not totally sure of. We might just consider adding a thicker, lower metallicity disk to our model. That might solve the problem. If that is the case, then there are probably going to be more lurking black hole candidates that we would expect to find, but just kind of something to think about. The takeaways that I want you to take away with this, though, just in this one small foray into this study, is that this population offers just a fantastically enormous wealth of opportunity to inform binary evolution models. And that's because we're getting to the binaries where there are more of them, and you can study them in great detail. The other thing to take away is that at present, we really favor basically no black hole kicks, but we aren't totally in tension with apogee yet. And I guess I'll just leave the takeaways here for now, and then we can just talk questions for the rest of the time.
Okay, thank you, Katie. Let's thank her. Okay.
Yeah, should we